Thank you all for joining us. As Nick says, what we're going to be doing today is to talk about a new method for sensitivity analysis to help us to avoid missed opportunities in our drug discovery projects. So just a quick overview of the talk. First of all, I'm just going to talk in general about some of the ways in which we make decisions about selection of compounds for a drug discovery project, thinking about target product profiles, and also in that context about what we mean in terms of sensitivity analysis. Then I'm going to give a short introduction to multi-parameter optimization in drug discovery, as this is a foundation on which the method is built, before focusing on sensitivity analysis itself and answering some key questions. For example, would a small change in the choice of selection criteria for our compounds have a big impact on the direction of a project? And really, this is about avoiding missed opportunities, maybe making sure that we're considering all reasonable routes for our project before focusing too quickly. I'll give an illustrative example of this using an example data set before drawing some conclusions. And as Nick said, I'll also be happy to address any questions that you have at the end of the presentation. So first of all, selecting compounds in the context of a drug discovery project. Sort of key concept here, and the key objective really in drug discovery, is this idea that's commonly described as multi-parameter optimization. We know that an efficacious and safe drug that makes it to the market and occupies a strong position must have a balance of many different properties. Obviously, potency against our target or targets, but also appropriate physicochemical, ADME, and safety properties. And we also know we typically start with a hit somewhere out here in potency space, but it's very unlikely to have all the properties that we require. So we want to move as quickly as possible to this sweet spot where we're most likely to find a successful drug. On the other hand, we want to identify those situations when that balance is not possible. As illustrated here, if the space that gives us potency does not overlap with all of the other properties that we require. And of course, the way this is very commonly described is, fail fast, fail cheap. Save our time and effort. Don't waste it on pursuing compounds that are destined to fail. But of course, we don't want to fail. The last thing we want to do is miss the opportunity to find a good drug. So really, we only want to fail when we're confident that that's the right decision, when all the data we have generated can convince us beyond a reasonable doubt that we're not going to find a good drug, at which point it makes sense to move on to a new chemistry, a new project, or a new target. And this is the idea of multi-parameter optimization. And of course, what that gives us is a very complex landscape of data in which we have to make very important decisions about the direction of our project. And of course, one of the very common ways for making these decisions is to define a target product profile, a set of criteria for important properties that we want to achieve in order to move forward in our project. And this is just an illustrative example of some criteria we might have for the hit to lead transition, where the goal of the project is an orally dosed compound. So we might look at properties, of course, the pharmacology, the potency against our target. Perhaps we would define a criterion of less than 100 nanomolars. But of course, we also want selectivity against closely related off-targets, and we might define that as a factor of 100, for example. But clearly, we also want good physicochemical properties, maybe a low log P and high solubility, and perhaps limit the size of our compounds by setting some molecular weight criteria. And if we're thinking about ADME, then clearly for an orally absorbed compound, we might look at something like CACO2 permeability in the apparent permeability, as well as microsomal stability to get a feeling for metabolic stability, particularly with respect to P450 enzymes. And of course, we might want to avoid active transport by P-glycoprotein. We might look at bidirectional transport across CACO2. Now, the importance of that criteria may also depend on whether we're looking for a compound in the brain or a peripheral target. And we might look at safety criteria as well, so avoiding drug-drug interactions mediated by P450 metabolism by limiting the affinity for the major drug metabolizing isoforms. clearly avoiding hERG inhibition to avoid potential cardiotoxicity into cytoplasm, and cytotoxicity, for example, in HepG2 cells. So these are just some examples. Of course, every project is different, but I'm sure you recognize some of these criteria yourselves. But when we're coming up with these profiles, we should ask ourselves some questions, because the choice of selection criteria is often subjective, based on experience of previous projects, for example, or knowledge of the disease and chemistry that we're working in. It could also be based on data for historical compounds, but of course, the number of successful compounds that reach the market is relatively small in comparison with the chemistry you might explore, and so the data we have is often very limited. So when we're defining these profiles, we need to ask ourselves some questions. Are we sure that the criteria we've chosen are the right ones or the best ones for our objectives? And if we're not sure, what impact would that have on the decisions we make if we've not chosen the right criteria? And most importantly, are we missing opportunities? Are there compounds or chemical series that we might have inappropriately discarded due to our choice of selection criteria? And that really is the goal of sensitivity analysis, is to address some of these questions before we proceed by applying these criteria for selection of compounds. So we might think of an analogy here. Maybe we're looking for a vacation, going on a perfect holiday. We want to find the right destination. And of course, we might go on a website like TripAdvisor, and we might look at lots of different factors. The location, of course, is very important. What country do we want to go to, or what region, for example? We might look at reviews of different criteria. So we might look at reviews of cleanliness of the venue, of how family-friendly is it if we're going with our kids. What are the amenities that are provided? We might look at how close it is to an attraction we're particularly interested in, either Disney World, or in this case, maybe we're interested in going to the beach. And so just to make our decision a bit simpler, we decide to only look at hotels within half a mile of the beach. We just filter out the rest, so we sort of limit the field. But we have to ask ourselves the question, what if an otherwise perfect hotel, sort of illustrated in this picture, was just 900 yards from the beach, just outside of half a mile? We might never have noticed it. We might never have considered it. And we have to ask ourselves, have we missed the holiday of a lifetime? The question is, in the terms we're talking about today, is how sensitive was our decision to this arbitrary criterion of half a mile? Now, mapping that into the drug discovery world, there are lots of applications of this. We might obviously want to spot any opportunities we might have missed. For example, we might choose that our progression criteria for the potency of our compounds is less than 10 nanomolar. But what if there was a series with good ADME and safety criteria in which the best potency was 50 nanomolar? Would we necessarily want to reject that? How arbitrary is that cutoff of 10 nanomolar? Now, in simple cases, we might be able to spot this quite easily, but with the increased size of libraries, the complexity of the data, the different endpoints that we're measuring, it can often be very difficult to spot this in practice. And also, as projects progress, we often forget about chemistries we've looked at in the past. And one scenario is maybe looking for potential backup series. As we're progressing our primary series into development, we want to look at backup series in case any unexpected issues come along. And looking back, it's often difficult to remember the details of earlier chemical series. We might want to look for some compounds that are slightly different from those we've considered for our primary series. And another very common scenario is to address disagreements between different project team members from different backgrounds or with different experience. For example, you might sit in a project team meeting and some people might say, well, we need to have 100 micromolar solubility to progress. Others might say, well, actually, we could probably get away with 10 micromolar. We don't need to be so ambitious. Now, the first question we might ask is, well, actually, does that difference in opinion actually matter? If both criteria would actually lead us in the same direction, we actually don't need to have an argument. That's absolutely fine. But on the other hand, if the criteria of 100 micromolar leads us in one direction and a criterion of 10 micromolar leads us in a completely different direction, then we need to very carefully consider those two options Or maybe even try a little bit of both, get some downstream data before deciding which of those criteria is the most important for our particular project, most relevant for our particular project. So these are some of the questions we're going to be looking at. And now, as I mentioned, just to lay the foundations here, I'm just going to spend a few minutes talking about multi-parameter optimization, on which this method is based. And so this idea of multi-parameter optimization and balancing many different properties, there are many approaches that have been used. I've just listed a number of them here, and I'm not planning to go through all of them today. That's not really the focus of today's presentation. But if you do want more details, then I'd refer you to one of our previous review articles, which goes through all of these methods in much more detail. But probably the most common approach to multi-parameter optimization is filtering. And I've illustrated filtering here as trying to find a diamond hidden in a pile of coal, where of course that diamond is the perfect compound that will become an ultimately successful drug. And if we were filtering, we might take a property, very commonly potency, and we would throw away the compounds that didn't meet our potency criterion, whether that be from our sort of high throughput screen or early primary assays or predictions from a model, for example. We take forward the ones that do. But we're not talking about just one property, we're talking about several. So for example, you might look at absorption. We saw CACO2 as an example before, and we throw away the compounds that don't meet our absorption criteria. And maybe we look at metabolic stability. Again, we saw before microsomal stability, and we discard the ones that don't meet our criterion for that. Now I'm showing 3 filters here, but as you've seen, we might have 10 or 15 different filters we might apply, and we hope that out of the bottom, our diamond emerges. Put that into development, and then 5 or 10 years later, we've got our successful drug on the market. We're all rich and famous. Well, of course, I don't need to tell you that it's never really that easy. For example, sometimes this happens, and nothing comes out of the bottom. And then we've got a big question on our hands. Is it because there was no diamond there in the first place? Are we in one of these areas of chemistry where all those properties just don't overlap? Or have we made a mismeasurement or a misprediction and incorrectly discarded that diamond somewhere in this process? And if so, where do we go looking for it in this big pile of discarded coal? And even worse is this outcome here, where incorrectly a lump of coal emerges from the bottom, and we spend months or even years desperately trying to optimize it, only to be destined for one of those dreaded late-stage expensive failures. And the question I'd like to raise is, well, how likely is this outcome? For example, if I had 10 filters that were each 90% accurate in making the correct yes-no decision, that's a very good scenario to be in. But in fact, in that case, the probability of that diamond emerging, even if it was there in the first place, is only 35%. That is, I'm more likely to reject my best idea than I am to keep it. And for that reason, we suggest that you treat filtering with caution. Sometimes it's necessary, but it's an approach that accumulates error without that being transparent. And there are a couple of reasons for this. There's uncertainty in our data in a couple of different ways. First is the uncertainty and the relevance of that property, of each individual property, to the ultimate outcome. So we've seen before a criterion for CACO2 permeation, for example, and of course CACO2 is an experimental model of human intestinal absorption. And maybe we would ideally like 50% or greater absorption in the clinic in humans. And if we look at some typical data here taken from the literature for CACO2, we often see this sort of pattern here, where on the x-axis we have the human intestinal absorption up to 100%. On the y-axis we have that CACO2 permeation. And a typical cutoff we might set here is maybe a PAP of 2 nanomolar per second. 2 nanometer per second, excuse me. And here you see above that, we get a very good result. Almost all of those compounds, in fact all of the compounds meet our criterion. But if we fail to meet that criterion, if we're below that value here, actually that doesn't tell us very much. There's a wide spread of human intestinal absorption. And so, we wouldn't necessarily want to reject a compound based on that. There's still a reasonable chance of achieving our goal. And if we look at that in a different way, and we look at the CACO2 apparent permeability along the x-axis against the proportion of compounds meeting our criterion, you can see there's not a hard cutoff where it's good or bad. In fact, there's something like this shape here where the worst place to be is below 0, but even there's maybe a 35% chance of success. The best place to be is above 2, as we've seen, but in between there's not a hard cutoff, but a sort of a trend there. And so we can represent that instead of a filter as something called a desirability function. And this is something that relates the property values themselves, how desirable that outcome is. So here's a very trivial desirability function which represents a filter where you say above our cutoff of 5, we've met our criteria, below we reject a compound. It has a desirability of 0, we would kill that compound outright. But instead of a hard filter, we can be more subtle. Maybe here we're saying we would ideally like to be above 5. That's our desired value where we get a desirability of 1. But below, instead of killing it outright, we can still say there's a reasonable chance of success. And so that doesn't get a 0, but it's still reasonably desirable. But instead of hard cutoffs now, what we can see is you could say a range. So between 4 and 6 here is ideal, and you can see above that is worse than being below that range. We still have hard cutoffs here, but now we're just defining a range instead. But now we can start to be a little bit more subtle. We could have an ideal value of 5, but instead of a hard cutoff now, we sort of get worse and worse and worse until we get too high or too low and reach our desirability of 0. Or a trend, as we saw in the previous example. So here, ideally greater than 8, but it's not a hard cutoff. It gets better and better and better until it reaches that objective. Or you can use nonlinear functions, and this is an example of something called Deringer function. And so now you can relate that each individual property to its desirability. We can then combine those into what's technically known as a desirability index. And there are two different ways of doing that. You can either add them together or multiply them to get an overall measure of the desirability of those compounds. And this has some benefits. We've avoided that hard sort of good-bad cutoff. It's also very flexible. We can define those trade-offs that we're willing to make for each of the properties. And it's also very easy to interpret because we can see the impact of each property, its desirability, on that overall priority we would give a compound. But although this is a step forward and removes that question of, or addresses that question of relevance, there's still another source of uncertainty, and that is the experimental or statistical error in all the data that we have. There's a lot of variability in the experimental endpoints. There's statistical error, certainly if we're using predictive methods. And so we might want to look at the impact of that as well. And so here we can see a very simple example. Again, I'm just going to use a cutoff for illustration. We have some cutoff here for some property, and we're saying we'd like to be to the right-hand side of that. That's our desirable outcome, and here is our undesirable outcome to the left. And if we had 3 compounds, A, B, and C, just shown by these vertical lines, what you can see is that C meets that criteria. It's the right side of that cutoff. A and B are to the wrong side. We would reject those. So that might be a decision we would make. Reject A and B and accept C. But that's only looking at part of the information because, of course, there's uncertainty in this data. We don't know those values perfectly. So we might look at compound A and see here that it has some uncertainty shown by this bell curve. And there you can see actually we're very confident the chance of it exceeding that threshold is tiny. So we could reject that one. That's great. But on the other hand, compound B, although it appears not to meet the criteria, you see from this uncertainty, there's actually a significant probability, that shaded region there, that it's good enough, that it does meet our criterion given that uncertainty. And for C, although it looks to be our best, there's again a significant probability here, the shaded region, that it doesn't meet our criterion. And so, in fact, a more appropriate decision is to, yes, reject A with confidence, but accept that we cannot confidently choose between B and C based on the available data. We would need higher resolution information or another criterion to choose between them. And another simple example, again, our cutoff here, maybe we've got compounds D and E shown here, both of which are the wrong side, the undesirable side of that threshold. But what if we had no choice? Those were our two best compounds. We had to pick one of them. Which would you pick? Now here you might say, well, E is closer to the threshold. That's great. Let's pick that one. But again, we might want to look at more information. Maybe we've got a lot of confidence in that value. We've got multiple experimental replicates, so the standard error in that is very small, and there's, again, a very small chance that it's actually going to meet our criteria. But perhaps for compound D, we've got greater uncertainty. Maybe we've only measured that compound once, and there's a much more uncertainty in that value. And so, in fact, the probability of it succeeding is higher. And so, in this case, a more appropriate decision might be to take compound D forward. It has a higher probability of success. Now, of course, we'd want to address that by repeating some measurements and getting that a tighter value for that property for compound D. But that might be a better investment of our resources, time, and effort. So the method that we're going to be using in the examples today is a method that we have developed called probabilistic scoring, which enables a project to define the profile of properties they require. This is a simple example here, defining their properties, the criteria, and the importance of each of those. And underlying each of these criteria is a desirability function, so that you can actually define those trade-offs and the relevance of each outcome. But what it also does is explicitly take into account the uncertainty in that data. So having taken your property data, whether experimental or predicted, assessing it against those desirability functions or criteria for success and the relative importance, it also considers those statistical or experimental uncertainties to calculate a score that represents the likelihood of success against that profile. That is the probability of achieving the ideal outcome. And what it also does is bring together all of that uncertainty to estimate the confidence in the overall score. So one way we can look at that is shown here. We've got a data set of compounds, just a small data set here, ordered by the score from the best on the left to the worst on the right. And on the y-axis we have the score itself. So here we have our highest scoring compounds. You see they've got about an 80% chance of success, which is really good. But what you can also see is an error bar around each of those scores. So what you can see is that overall uncertainty. And so that there's much more information here. For example, if we look at those top 5 compounds, you see their error bars overlap almost completely. But what that means is that the data we have so far do not confidently distinguish between those compounds. I can't tell you that compound 1 is the best here. We just don't have the evidence for that decision. We might need, again, some better data with smaller error bars or another criterion to choose between them. On the other hand, roughly the bottom 50% here, you see the error bars don't overlap. We can be confident these are not going to be as good as our best. We can reject them, save that time and effort, and maybe explore this chemistry further or get some additional data before making a confident decision. So this is a very rigorous way to prioritize the compounds for your project against the objectives that you have set. So that's the foundation on which we're going to base the sensitivity analysis. And the examples that I'm going to show you are actually based on probabilistic scoring, but please do be aware that they will apply to other approaches that are based on desirability functions to calculate these multi-parameter scores. So, the objectives of sensitivity analysis, be a bit more specific, are to identify the property criteria to which the selection of compounds is sensitive. That is, if we make a small change to that criterion, would it dramatically change the decision we would make about the compounds we're progressing? Those are the ones we need to consider very, very carefully. A secondary question, though, is to find the range over which the variation in a criterion has a negligible effect on the selection of compounds. So if all of the reasonable values lie within this range, then we can proceed with confidence. No reasonable value is going to significantly change the decision we would make. But if there is a significant change due to one of these variations, we want to identify the compounds that affects. those compounds for which the priority changes significantly due to a small variation in that criterion. Those are the compounds that may represent missed opportunities we might like to look at in more detail. So just to summarize the methods, what we do is to consider the impact of small perturbations in each desirability function underlying each of the selection criteria. So we look at small increases or decreases in that desirability function around the original, which is shown here in bold in the middle. And what we do is, for the original and the perturbed scoring profiles, we calculate the scores and rank the compounds and compare those ranks by calculating a Spearman's rank correlation coefficient, which is shown here as rho. And then the sensitivity is simply given by 1 minus rho. If it's a very high correlation between the old and the new, there's a very small change, and so 1 minus, that will give a correlation coefficient of 1. 1 minus 1 is 0, means it's just not sensitive. But if there's a dramatic change in the ranking, that will give you a low correlation coefficient, and hence 1 minus rho will give you a value close to 1, indicating high sensitivity. I'm not going to go into all the details of the underlying mathematics here, but I'll give you a reference at the end where you can look up more details. But we have some additional considerations we need to take into account because, for example, we're actually only interested in whether the order of the top rank compounds change. If the order of compounds that we would have rejected anyway change, we don't care. We would still reject them. So we actually only want to consider the top n compounds. We can define what that is, and the default here is to look at the top 10%. Also, we've talked a lot about uncertainty. We need to think about whether the changes in the order are actually within the noise. If they're just changing within the error bars, essentially, this doesn't actually change the decision we would make. It still tells us we can't choose between the compounds. And so what we actually do is correct the Spearman's rank correlation coefficient for the underlying uncertainty. And here's just a very quick example. If we look at the top graph here is our original scores on the left for just 3 compounds, A, B, and C. You can see there's quite big error bars around those. A is the best down to C. But maybe if we make a small change in one of these desirability functions, it reorders these compounds so that B is now the highest. But you see now, given those error bars, in fact, they still overlap, and so really we can't tell between these compounds in the original or the perturbed profile. And so in fact, the sensitivity that would be given here is 0. It's all within the noise. On the other hand, if we had higher confidence in those scores, you can see the smaller error bars here, then that change in order is significant. We've gone from choosing compound A to choosing compound B, and therefore this shows up as a much higher sensitivity. And the final consideration here is, of course, that we can only do the sensitivity analysis based on the data we have so far. But as our project progresses, we have more compounds, we've measured more properties, the sensitivity may well change. And so we want to be able to run this fairly routinely and be able to easily run and interpret the results and see if our decisions might have changed. Again, maybe looking back at potential backup series as we go through our project. And then, of course, we want to interpret the results, so there's a number of different ways to do that. First of all, for each of the properties, we get a sensitivity with respect to changing the value of that criterion, and also the importance of the criterion. As I mentioned, those are just numbers between 0 and 1, and you see this is rank ordered so that the most sensitive is here at the top. But we might also want to drill down and look at that sensitivity for an individual parameter. And so here what we can see for that potency here, you see there's a high sensitivity. This is the 0 perturbation. I haven't changed my criterion, but even if I shift it just a little bit up or down, this gives me a very high sensitivity. And so just small changes in that criterion for potency will have a significant effect. The range here over which we can vary that is very small without having a big effect. And if we look at maybe an individual example of perturbation here of just about 1 log unit, we can actually then see what effect that has on the compounds we would select. So which compounds change priority as the parameter varies here. And so you can see some of these compounds that are very high in terms of the original score are now very low in terms of the score for that small change in the criterion for potency. So we can find those compounds that are very sensitive. So that's the theory, that's the concept behind it, and what I'm just going to do in the next sort of 5 or 10 minutes is to show you an example of this in practice. So just to introduce the example, we have here an example data set that represents a scenario of a hit-to-lead project targeting an orally dosed compound for a CNS target. The data set I'm going to show you in a moment has 284 compounds in it, representing 6 chemical series. I'm just showing these as stacks in our card view in StarDrop here to show you the 6 different series with an example of each. And on top of that, you can see just the distribution of that primary potency for each of those chemical series. And that is a measured potency value. It's a pKi value against a therapeutic target. And that's been supplemented with QSAR predictions for some of those key physicochemical and ADME properties. And what we're going to do is look at ways we might choose to select compounds from that data set, and then the sensitivity of that selection to the specific choice of criteria. So rather than show you a lot of slides, what I propose to do is actually show you an example of this in our StarDrop software, just a little bit more interesting. So just to explain what we have here, this is the data set, as I mentioned, 284 compounds, and you can see here there's the experimental potency and many of these different parameters, these different calculated properties we might be interested in. Of course, this could all be experimental data if we wish, but early on in a project we don't have a lot of experimental data. And you can also see here we've scored these already against the profile that was chosen for this project. What you can see is that the project is looking for a potent compound, good solubility for orally dosed compound, of course, good human intestinal absorption, the right range of log P, blood-brain barrier penetration, and so on down the list. And they've defined their criteria and the importance of each. And of course, the most important of all is the potency. We must have a potent compound. And just to illustrate that, what you can see here underlying these criteria are these desirability functions. And so although our ideal result is better, the pKi of greater than 9, so that's better than nanomolar potency, we don't have a hard cutoff. We have a soft cutoff between 8 and 9, increasing that as a trend. And these have already been sorted. And just to show you, this is the sort of plot I showed you in my presentation. We have the compounds ordered by the score, the best on the left to the worst on the right. And I've colored these by the different series. So you can see here, purple ones at the top here are aminotetralenes. We've got some nice yellow ones, arylpiperazines, and so on down this list. So there's quite a distribution of different series that score reasonably well. But chosen these criteria with which to choose our compounds. But again, we want to ask this question: how sensitive is that choice of compound to the criteria that we've chosen here? And so now what we can do is actually run this sort of sensitivity analysis that I've illustrated. If I just click for a moment, it'll just take a moment to run that. And now you can see the output similar to the examples I showed you on my slides. Here you can see at the top are the table of those sensitivities, both to the value and the importance that we've given to each criterion. And I guess similar to the example on my slide, you see the most important criterion here is the pKi. And by selecting that, you can see this graph here. Just a small increase or decrease in that would actually lead to quite a lot of sensitivity in the decision we would make. So we don't have a lot of wriggle room here, if you like. We would need to consider that very carefully. And indeed, if we shift that by about 1 log unit, I can just select here and you can immediately see there's a group of compounds. If we were to reduce that criterion by about a log unit, would significantly increase in terms of the priority that we would give them. Again, those might be those missed opportunities. If we look at another criterion, just to show you an example of something that's not very sensitive, here you can see the importance of the blood-brain barrier penetration. Although it looks quite steep, I'll point out that the axis here is not going all the way up to 1. So let me just change that axis so you can see a reasonable comparison. And now what you see is a very flat curve. What that's telling us is we can change that importance quite significantly, bad choice of words, excuse me, quite dramatically, and have only a very limited effect on the choice of compounds. Here you see if I click one of the ones out here, basically there's a high correlation there. We would still choose the same compounds even if we made the blood-brain barrier penetration much less important or much more important. What that's telling us is for this specific data set that blood-brain barrier penetration is not having a significant effect on the choice of compounds. It might change later on if we had new compounds and new data, but so far we can be pretty confident that we don't need to worry about that criterion. So what we've seen there is that the PKI is very important, and a small change in that PKI criterion would have a significant effect. So let's see what impact that would have on the decision that we would make. And to do that, I've prepared a new project profile. It's identical to the original. If I select it, except very subtle change, I've moved this criterion to ideally greater than 8. Again, I've just shifted that desirability function by 1 log unit, as was suggested by the sensitivity analysis. And if I now run this new scoring profile, generate a new score, some compounds don't change very much, but others do. And indeed, if we go to the visualization, we can just have a quick look. And you see this sort of scatter plot, very similar to the one we saw in the sensitivity analysis tool. But now you can actually see I've colored these again by chemical series. Some of these green compounds begin to pop up. That's quite interesting. One way we might want to look at this, for example, is just in this sort of card view here. So here I have all the compounds represented by little cards. And as I showed you in my slides, we could stack those up by the chemistry. And so here you can see the 6 different chemical series represented by stacks of cards. And again, showing a representative structure, but also a histogram showing the distribution of potency. And so the question is, would it change the series that we would choose in this Hit to Lead project? So maybe we've got just under 300 compounds here, so maybe we choose 30 of those. Let me just select the top 30 compounds based on the value of that original scoring profile for our project. And if I select those, what you'll see is that they're highlighted here in the sort of cards. The little blue lines show us how many compounds have been selected, and what you can see is it's actually selected a few compounds from 3 different series here, the aminotetralenes, the aryl-piperazines, and the 2-aryl-cycloalkamine-1-indinol series. But if instead we choose to select by this slightly perturbed profile, I click select here, now you see quite a different outcome. In fact, we haven't picked any from this 2-aryl-cycloalkamine-1-indinol series, but instead it's prioritized this aporphine series based on a relatively small relaxation in the potency criterion for this project. This gives us access to chemistries perhaps with better ADME and physicochemical properties. So there's 2 possibilities. Either we need to work out which of those criteria are the most important, the most correct, I guess, or maybe we should actually select a few of these aporphines and a few of these 2-aryl-cycloalkamine-1-indinol compounds, get some downstream data, and then we'll know with confidence which of those series will yield us high-quality leads. So it's challenging our assumptions and making sure we're not missing opportunities. So back to the slides just for a moment, and I'll just bring those up. So this is the sort of outcome that we've seen, where we could actually lead us to quite a dramatic change in the strategy for our project, rejecting one series over another, for example. And that is something we'd want to consider carefully in the context of our project. So in conclusion, whenever we're making decisions in terms of the selection of compounds, we want to make sure that they're robust to the criteria we use. Because, as we say, these criteria are often subjective or based on limited and sparse data. Are these choices of criteria distorting the selection of compounds for our project? And I hope I've illustrated briefly that this idea of sensitivity analysis provides a very rigorous way to identify the criteria which are sensitive, and those are the ones we want to consider carefully, or maybe explore different alternatives before deciding which one is the right criterion. And along the way, we've also discussed the importance of the uncertainty in the data, because we have to remember that all the data we make these decisions based upon have significant experimental variability and statistical error. Now, I promised you I would point you where you can find more details. So here you can see a link to a preprint of an article on this topic, which has more of the details of the methodology than I've covered in today's presentation. And in fact, purely by coincidence, the paper was just accepted by the Journal of Medicinal Chemistry yesterday and has appeared in an initial preprint form on their website today. So whether you get it from our website at this link or Journal of Medicinal Chemistry, I hope that you'll find it interesting. And on that note, I'll draw a conclusion to the presentation and be very happy to address any questions that you may have. Yes. So there is a question. Can the same results be derived from the weights? That is the importance of each of the criteria. That's an excellent question. It is one that I maybe brushed over slightly in the interest of time when talking about the methodology. Let me just jump to an appropriate slide to answer that. Right. So in one of these profiles, you can not only define the criteria in which you're interested, but also the importance or the weight that you would give to that criterion. And in the methodology that I described, I was focusing on shifts to the value in that criterion, so moving up and down the scale of property. But actually, the importance is related to the difference between the ideal outcome and the worst possible outcome. And so in fact, what you can also do is apply that same idea to a scaling of the desirability and look at the sensitivity of the decision you would make to that weight or importance for each of the properties. So yes, absolutely, you can do that. And in fact, again, I didn't focus on it, but as well as giving a sensitivity for each of the values, you can also give a sensitivity to the importance or the weight given to that criterion. Another question, does the range of each property also come into play? Absolutely. The sensitivity of the decision you would make will also depend on the range of the actual values in your data set. So, for example, if we have this criterion here shown by this sort of black desirability function, if all of your compounds were up here with a very high value, then clearly changing that cutoff or that desirability function won't have a significant effect at all. Whereas if your property values actually spanned that desirability function, then that's where it can become very sensitive. So there are many different factors that come into play as to whether a criterion will be sensitive or not, and that's why it's important to be able to analyze that in a very rigorous way. It can be very difficult indeed to spot by eye. Well, thank you all very much again. Unless any questions come in the next sort of 10 or 15 seconds, I think we'll probably end it there. I hope that's been very interesting. Let me just jump to my final slide again to remind you of where you can find a more detailed preprint that covers all of this. If you do have any questions after the fact, you're very welcome to email me. My email address is very simple. It's matt, M-A-T-T, @optibrium.com, and I'll be happy to discuss this further.